Hello to everybody, I'm Dr. Mehdi Mehrabi and I'm the course coordinator of MHM 427AT. Welcome to the course. I hope this semester will be a success and I count on your efforts for that. Let me start with a bit of housekeeping information. Our main textbook is the 5th edition of Heat and Mass Transfer Fundamentals and Applications, Senjalan Gajar, McGraw-Hill publication. You are familiar with this textbook. You used it during MTV 410, I guess, if I'm not mistaken. We also have 2 ebooks available free of charge online. There are supplementary resources, so don't worry about it. Anytime that you need to go and read, I will let you know. So the main focus, all the assignment, everything will be from the main textbook. For this course I'm going to have teaching assistants, but the information regarding them will be available on ClickUp. Besides that, please go to the ClickUp, go through the study guide to have a better understanding about the expectation from my side, as well as the rule of assessment, how many class tests you are going to write, how many assignments I'm going to give you, how I'm going to calculate the semester mark and final mark and everything. As you can see here, this course consists of 4 study themes: fundamental of thermal radiation and radiation heat transfer, boiling and condensation, fundamental of mass transfer, and heat exchangers. Let's start with the first study theme, which is the fundamental of thermal radiation and radiation heat transfer. For this study theme, we start with an introduction to thermal radiation, and after that we will speak about electromagnetic wave spectrum. Then we carry on to the next subsection. We will spend quite some time on blackbody radiation. When we are done, we move to the next subsection and we speak about solid angle, irradiation, and radiosity. Then we continue our lectures on radiative properties of materials. We will talk about emissivity, absorptivity, reflectivity, and transmissivity. We will go through Kirchhoff's law, and then we study about greenhouse effect, and at the end of this section we will speak about atmospheric and solar radiation. But let's go one step back. Do you remember 3 modes or methods of heat transfer? Let me write it down here for you. Conduction, convection, and radiation. If you recall, the conduction was the heat transfer. How? You remember that? Yes. The transfer of heat between atoms as they collide within a substance. Okay, within a substance. How about the convection? Convection heat transfer was the movement of matter due to differences in the density that are caused by the temperature difference. And radiation is the transfer of energy by the electromagnetic waves. All of you are familiar with these 3 concepts, but there is, I would like to emphasize on very important information here. Radiation is very unique compared to the rest of them. Unique. I understand that there are 3 different modes of heat transfer. They have their own characteristics and differences. But radiation is unique compared to conduction and convection. Do you know why? Because radiation is the only method or modes of heat transfer occurs in a vacuum. Only modes of heat transfer occurs in vacuum. So what does it mean? So it means that radiation is the only heat transfer mechanism that does not require any material medium to happen. Okay? Interesting. Okay, now we just talked about that radiation heat transfer is the only modes of heat transfer that does not require any medium to happen. Okay, so how we can define radiation heat transfer then? So basically we can define the radiation as thermal radiation. Radiation is electromagnetic radiation emitted by a body due to its temperature. Can use this definition for thermal radiation. So, but you see here, we are speaking about electromagnetic radiation, okay? But at the same time, we said that radiation is the only mode of heat transfer occurs in vacuum. So, what's the electromagnetic radiation in a vacuum? We want to talk about it. So in order to talk about it, we need to first speak about the speed of light in vacuum. Am I right? So if you recall, this is the speed of light, and we know that the electromagnetic radiation in vacuum travels with the speed of light. Okay? So electromagnetic radiation in vacuum travels with the speed of light, and that's the speed of light. Okay? But we are not always facing stories in vacuum. Sometimes it's the bodies, especially now, let's say, in our daily life. We are facing with materials that, or situations that the radiation is happening not just in vacuum, but in the normal materials. In order to sort the problem out, we define one index called index of refraction. How we define it? C0, which is speed of light in vacuum, to C, which is the speed of light in the medium. Of light in the medium. Okay, so based on this index, we are expecting that for the normal materials, the index of refraction is higher than 1. But let's give some example. For example, for water, this index is around 1.33. For glass is equal to around 1.5, and for air or gases is around 1. Okay, so for air or gas, we assume that the speed of light in air or gases is more or less the same as the speed of light in vacuum. Okay. This is figure 12.3 of your textbook. This figure shows the electromagnetic wave spectrum. In this chapter, we are focusing on like a special wavelengths that I have highlighted with yellow for you. So this yellow highlights is between 0.1 micrometer to 100 micrometer wavelength. We call this boundary thermal radiation. And our focus in this chapter will be on this area which is highlighted with yellow. So it's a bit of UV, visible light, as well as infrared. Okay. How about the visible? The boundary for visible light, it's between 0.4 micrometer to 0.7 micrometer. Visible light. The another boundary which is important for us is between 0.4 micrometer to 3 micrometer, which is solar radiation. Please do not mix these two concepts. Solar radiation between 0.4 and 3 micrometer, thermal radiation between 0.1 and 100. Okay, so our focus in this chapter will be on this wavelength boundary, which is the thermal radiation. Okay. But now it's time to speak about how black body emits radiation. Let me start with the law which is called Planck's law. Okay, we are going to talk about it, but you might say that, okay, you didn't say anything about black body. What is black body? How we can speak about how black body emits radiation without knowing what is the black body? You are completely right, but because black body is a complicated concept, just have this Planck's law first, and after that, at the end of this lecture, I'm going to define the black body as well. Okay, so don't be worried, we are going to speak about it. Okay, the Planck's law is saying that E B lambda and T will be equal to constant C1 divided by lambda to the power of 5 E C2 lambda T minus 1. Okay, so C1 and C2 are both constant, and you can find their value in your textbook. But how we are going to read this one? So EB lambda. So of course we know that the E is emissive power. So E emissive power. B stands for black body. Black body, and lambda shows that is a function of wavelength. So if we want to read it, the EB lambda will be read as spectral, which means function of wavelength, black body emissive power. Okay, spectral black body emissive power. So emissive power in his nature is a function of temperature. We have it here. And because it's spectral, so it's a function of wavelength as well. So Planck's law is saying that a spectral black body emissive power, which is a function of lambda and temperature, is equal to correlation, which the correlation has two constants. We can find those constants, and at the same time lambda and e to power of c2 divided by lambda t minus 1. Okay, so Planck's law is showing or telling us how a black body emits radiation. We are going to use this law, so keep it in mind. Okay, let's go to this slide. What you can see in this graph, so we can say that, okay, as the temperature goes up, it looks like that the black body is emitting more energy. Well, that's something that we expect, am I right? So you see that here, this picture shows that EB lambda, spectral black body emissive power, versus wavelength. Okay? So what we see, when the temperature goes up from 100 here, 300, 500, 1000, 2000, 4000, and 5800 Kelvin, we see that the black body is emitting more energy, which is logical, because the hotter something gets, it's going to emit more thermal radiation. Okay, so in a nature, radiation is a function of temperature. No problem about it. What else we can see from this from this graph? So you see that there we have temperature constant curve. So for example, here you see that for the temperature of 100 Kelvin, we have a temperature constant curve. Okay, so you see that for any temperature constant curve, we have a maximum for all of them. So for any temperature constant curve, we have a maximum. Okay, but maximum happens at a different wavelength, which is important as well. Just look at this one. I just highlighted the maximum emissive spectral black body emissive power for you, and you see that when the temperature is high, this maximum spectral black body emissive power happens at shorter wavelengths. Okay, that's what the picture is telling us. The other story is, most probably you say that, okay, we can see it, but how about this wavelength? We want, most probably, because it is important for us to know where this, like we are saying that the maximum, for example, for the temperature constant at 100 Kelvin, the emissive power goes through a maximum value. Okay, but we want to know that where this maximum value happens, at what wavelength. We call this wavelength at lambda max. Okay, so in the next slide I'm going to show it, and I'm going to tell you how to calculate it. Okay, so look at that. This is one like a constant temperature curve. We are saying that, for example, okay, here is the maximum. This maximum is going to happen at a wavelength that we call it lambda max. This lambda max, it doesn't mean that the wavelength is maximum. This lambda max means that at which wavelength the spectral black body emissive power is maximum. How to find it? By using Wien's displacement law, Wien's Means displacement law. So basically what this law is saying, that is saying that the lambda max multiply T is equal to the constant, and that constant is equal to 2897.8 micrometer Kelvin. Okay, but please keep in mind that delta lambda max here is not the maximum wavelength. It is the wavelength at which the emissive power, or spectral blackbody emissive power, is maximum for a given temperature. Just think about that. For example, like let's say the temperature is 200 Kelvin, and we want to know that at what wavelength the spectral blackbody emissive power is maximum. Easily we just put it into the Wien's displacement law is 2897.8 micrometer Kelvin. Always use the unit is equal to 14.49 micro. Okay, so as simple as that. Now let's go to the next slide and see. We talked about Planck's law and a spectral blackbody emissive power for a given temperature. If we integrate for all possible wavelengths, which would be the area under the curve here, integrate for all the wavelength, we will have the blackbody emissive power. Am I right? So we have a spectral blackbody emissive power. If we integrate it for all the wavelength, we will have EBT. Okay, so EBT is equal to integrating for all the wavelengths of EB lambda and T d lambda. Do you agree with me? Okay, so now let's do this integral and see what we get at the end. You remember this one from the Planck's law? Planck's law. I told you that EB lambda and T is equal to C1, which is like a constant, lambda 5 e to power of C2 divided by lambda T minus 1. Okay, so we have the Planck's law, and at the same time we know that if we integrate the spectral blackbody emissive power for all the wavelength, we will have emissive power, blackbody emissive power. Let's do this integral and see what we can get. Okay, so EBT is equal to 0 to infinity. I just put the Planck's law here. C1 lambda 5 e C2 lambda T minus 1 d lambda. Okay, so to make it easier, we just like do a bit of math manipulating. So if we assume that C2 lambda T is equal to x, okay, we assume that it is x. What we get? What we are getting is, so lambda will be equal to C2T 1 divided by x, and d lambda will be C2T minus 1 x2 dx. Okay, so if we substitute this one into the main integral, we will have y happen infinity to t, because we said that the lambda is between 0 to infinity. So if we want to write it based on the delta x dx, based on dx, when the lambda is going toward 0, the x is going toward infinity, and vice versa. So infinity to 0, we just put, we keep the c1, lambda 5 goes high, minus lambda 5, e to the power of x minus 1 dx. Okay, we didn't do any extraordinary, we just put this one here, substitute this with x. Okay, we just use this substitution. So instead of using this like a long correlation of C2 divided by lambda t, we just use it x. So e to power of x minus 1 d lambda, we just said that dx here, okay? But we need to add these terms into it as well. So c2t minus 1 x2. Okay, so basically this one was d lambda. So it's basically is the same. We are just like substituting different things. Okay, let me go to the next slide and continue. So we finished the previous one with this one. Let me just put it here. EBT was equal to infinity to 0, c1 lambda minus 5, ax to 1, and after that we said that it's c2t minus 1 x2 dx. Okay, so we have x2 ax minus 1 dx, c1 c2. The only thing that we need to change is lambda to the power of minus 5. So here we have a minus, we can apply it into the boundary, so it will be 0 to infinity again, c1 c2 lambda minus 5 t ax minus 1 x2 2 dx. Okay, so let me substitute the lambda as well, so it will be equal to 0 to infinity c1 c2 minus 5. We are just substituting t ax minus 1 x2 2 dx. Okay, so this will be equal to 0 to infinity c1 c2 t5. Am I right? Yes. c2 to the power of 5, because it was minus 5 on top, will go down, multiply by t, stays here, x goes up 5, x2, so it will be x3 on top, ax minus 1 dx. Okay, so to continue, we will have EBT equal to 0 to infinity c1 c2 t5 divided by c2 to the power of 5t x3 ax minus 1 dx. Okay, So this one, just look at that. We said that C1 and C2 are both constant. So constant, constant, constant to the power of 5. Temperature, so it's constant. So again, the whole thing is constant. So can come out of the integral. So EBT is equal to C1 T4 C2 to the power of 4 integral of 0 to infinity x3 ex minus 1 dx. Okay, this is an standard integral 0 to infinity x divided by x e to the power of x minus 1, and it's equal to pi 4 divided by 12. So we have this one. We have from the textbook C1 is equal to 2p h CO to the power of 2, h heat transfer coefficient, c the speed of light in vacuum, and C2 is h CO, k h the same heat transfer coefficient, k thermal conductivity. If we put everything in together, EBT will be 2 pi 5 K4 15 H3 C to the power of 2 T4. That's the final answer that we get. Okay, but look at that. That looks a bit familiar to you, no? I think so. So let me just rewrite it and see what we get. So it was 2p5 k4 divided by 15h3c t4. Okay, we call this one sigma, Stefan Boltzmann. So EBT is equal to sigma t to the power of 4. Yeah, so black body emissive power, body emissive power. So what we did is we did the integration for all the wavelength to get from spectral black body emissive power to black body emissive power. So the black body emissive power just is the function of temperature, nothing else. Like a constant multiply by temperature to the power of 4. This Stefan Boltzmann constant and it's equal to 5067 10 to the power of minus 8 watt 2k4. Just be advised that when you are using this correlation to calculate the black body emissive power, temperature should be always based on Kelvin. Okay, so now you saw that how easy it was. We just like integrated for all the wavelength, and now we can calculate the black body emissive power. This is called Stefan Boltzmann Law. So Stefan Boltzmann Law, which is saying that the black body emissive power is a constant temperature to the power of 4. Okay, so we talked, just like we finished speaking about the Stefan Boltzmann law. To get to Stefan Boltzmann, we integrated for all the wavelength. But sometimes it's necessary to know the fraction of the total emission from a black body that is in a certain wavelength intervals. So we are not interested for all the wavelength, we are just interested for a specific wavelength. Okay? For a given temperature and wavelength intervals of 0 to lambda, let's say, we want to integrate between 0 to lambda. So 0 to lambda. We have lambda, 0 to lambda. Okay? What we do? So we just do the integration between 0 and lambda. Okay? So basically, EB T for 0 to lambda will be 0 to lambda EB lambda T d lambda. Okay? As simple as that. But the other story is, we already calculated for all this area. We calculated, we did the integral. So instead of doing this integral from the scratch, we can say that we can define something which is called black body radiation function. This is saying that F lambda T, so the black body radiation function from 0 to lambda, as I said, is 0 to lambda EB lambda T divided by the first integration, the whole area is like a ratio, so sigma T to the power of 4. Okay? So the black body radiation function will give the ratio of the emissive power of that specific area to the whole area, which is 0 to lambda EB lambda and T d lambda, of course I forgot to put it here, divided by the whole integration that we just calculated, which is sigma T4. So you might ask that, okay, what about if we have two intervals like here? We are not interested between 0 to lambda, we are interested between lambda 1 and lambda 2. How about that? Okay, for that one, we use the same concept. So we say that the black body radiation function of F lambda 1 minus lambda 2T. So lambda 2, 0 to lambda 2, EB lambda T d lambda minus 0 to lambda 1, EB lambda T d lambda divided by the whole area, sigma T4, which is F lambda 2T minus F lambda 1T. Yeah? So basically what we are saying that here, if we have AB lambda is like something, and we are interested between lambda 1 and lambda 2. So first we say that, okay, first we calculate between 0 to lambda 2 this area, and after that we divide 0 to lambda 1 this area. The remaining area is what we are interested, which is between lambda 1 and lambda 2. We just put it into the integration between 0 to lambda 2 for getting that area, and after that minus 0 to lambda 1 between this area. What we get is between lambda 1 and lambda 2. So this one basically is the definition of black body radiation function. We put it here. Again, the same thing, minus sigma T4 can be here. Again, that's the definition of black body radiation function, and it will be lambda 2 if we just put the minus here in the middle. we divided to two different terms. Okay, so that shows how we can use the blackbody radiation function to calculate the blackbody emissive power without using complicated integration. Okay, now we talked about it, but let's say, what is blackbody? Let's define blackbody for us. Okay, blackbody is simply can be characterized by three terms. Okay, so we can categorize blackbody by three terms. First, let me write it here, blackbody. So instead of defining it, we are going to speak about the characteristics of blackbody. First, the best possible emitter. So what is the first characteristic of a blackbody? Blackbody is the best possible emitter. 2. Blackbody absorbs all the incident radiation. And the third one is blackbody is a diffuse emitter. What does it mean? It means that it is independent of direction. These three terms implicate that reflectivity and transmissivity for a blackbody is 0. Later in this chapter we speak about it, but have it for now that a blackbody for a blackbody both reflectivity and transmissivity are 0. Beside that, blackbody, we need to think about that the blackbody is a model, and it's hard to build or have a blackbody in reality. Not hard, maybe impossible. Let's say we have a perfectly flat plate and we paint it with the best black color which is available in the market. The plate might absorb 90% of the incident radiation, but not 100%. Okay? So again, keep it in mind. The blackbody is a model. Why we are studying it? That's another story. I'm going to talk about it because we want to have a reference, and after that compare the normal situation or normal material with blackbody, because we have a maximum value and we know that for normal material we will get less. Okay? But in order to speak about like a concept, let me give you some detailed information about it. Just let's consider that we have an evacuated enclosure. So its inside is vacuum. Okay? And the enclosure is at a temperature of T infinity. At a temperature of T infinity. Okay? I put a black body with initial temperature of TW inside this enclosure, which TW is greater than T infinity. Okay? So I'm saying that the radiation is the only form of heat transfer. Why? Okay, I said that it's evacuated, so inside is vacuum. No convection. Why? Because there is no matter. Okay, no convection. And since I put the black body inside the enclosure in a way that it's not touching the body or like the walls of enclosure, there is no conduction. So no conduction, no convection. The only form of heat transfer which is left is radiation. Okay? We assume that our black body is very small and our enclosure is at infinite heat sink, which means that the heat received from our small black body will not affect the enclosure. Maybe like, let's say, putting a small coin with a temperature of 100 in the middle of big swimming pool. So that's the concept of infinite heat sink, which means that the heat received from or a small black body will not affect the whole enclosure. Okay, so what will happen after sufficient time has elapsed for black body? So let's say it's temperature of black body. This is the time. It starts as TW. The enclosure has a temperature of T infinity. So because the enclosure is at infinite heat sink, this will be what we are going to have. So after sufficient time has elapsed, eventually the thermal equilibrium will take place and the black body will achieve equilibrium with its surrounding inside the evacuated enclosure. Okay, here now we can say that, okay, now we have the thermal equilibrium established inside the enclosure. Looks very simple, but what does it mean we reached to thermal equilibrium? It means that the black body absorbed the same amount of radiation that is emitted. Okay, what we are saying that? We are saying that, okay, black body has a temperature TW greater than T infinity. Okay, because of its temperature, it's going to emit. Am I right? So, but in order to reach the thermal equilibrium, it has to absorb the same amount of radiation that is emitted. Okay, so the black body absorbed the same amount of energy radiation energy, we can say the radiation that it emitted. Okay, maybe you say that no, I'm saying that no, the black body did not absorb the same amount of radiation that it emitted. Okay, so it says like a statement, we should be able to prove that. Okay, let's say if the emission is not equal to absorption. Because I claim that based on all the stories that I said that, okay, the black body reached thermal equilibrium with its surrounding, and in order to do that, it means that the black body absorbed the same amount of radiation that it emitted. But we say that, okay, just think that no, it's not true. So if the emission is not equal to absorption, so what would happen then? In this situation, we should have a net rate of change of enthalpy. Am I right? So if emission is not the same of absorption, we should have a net rate of change of enthalpy. Okay, where this net rate of change of enthalpy should occur inside the black body. Okay, so if the emission is not the same as absorption inside the black body, a net rate of change of enthalpy should occur inside the black body. And from thermodynamics, you are agree with me that when we have a net rate of change of enthalpy, it means that we do not have thermal equilibrium. So we won't have this one, no thermal equilibrium, which is against what we said at the beginning. Okay, so easily we could prove that if the thermal equilibrium is achieved, the black body must absorb the same amount of radiation that it emitted. Okay, it's simple. Maybe you feel it a bit complicated, but just like play the video one more time, think about it, you will get it. It's easy. If I want to say it in an easier way, I can tell you that the black body has achieved equilibrium with its surrounding. Okay, we just use this concept of heat sink, like sending a hot coin inside the swimming pool. What will happen to the swimming pool? Nothing. What will happen to the coin after sufficient time elapse? It will get to thermal equilibrium with its surrounding. So the same concept. Okay, so the black body has achieved equilibrium with its surrounding. No convection, no conduction. The only form of heat transfer is radiation. So the amount of radiation emits should be the same as absorption. And since we said that the black body is a perfect emitter, it needs to be a perfect absorber too. Okay? The other thing that we need to prove is the black body is a diffuse emitter, because we said that black body is a diffuse emitter. Is a diffuse emitter. So we want to prove that. But what does it mean, diffuse emitter? It means that is like first we need to speak about the radiation isotherapy. Okay, so we want to prove that. Okay, but first we need to speak about radiation isotherapy. Okay, so let's say we have two evacuated enclosure, exactly like the first one, as I mentioned, both of them at T infinity, but it's like completely okay. So again, the same concept. I put a very small black body with a temperature of TW here and the other one here. Not in the same position, different position. And inside both of them is vacuum. Will it change anything? Like the position of black body will change anything that I just said about the thermal equilibrium with its surrounding? No, it doesn't matter. It's exactly the same as, but let's go back to the same example, like a coin. Really matters which exact location that you put a coin inside the swimming pool? Not really. The same thing will happen. It will reach to the same thermal equilibrium when after enough time lapse, the temperature of the black body will be the same as T infinity. So now we can say that regardless of the position of the black body inside the evacuated enclosure, regardless of the position of the black body will reach the same equilibrium temperature. Okay, and when it reaches the equilibrium, the emission will be equal to absorption, because we just talked about it, and that will be the maximum corresponding to the temperature of T infinity. Why? Because it's black body. We said that the black body is a perfect emitter. Perfect emitter, what does it mean? It means that for a given temperature, black body emits the maximum amount of radiation. Nothing in the world can emit more than a black body at a given temperature. Okay? So basically it's proved. So we proved the radiation isotherapy, that regardless of the position of the black body will reach the equilibrium temperature. Okay? Now let's use this concept of radiation isotherapy and try to prove that the black body is a diffuse emitter. Okay? So basically the radiation isotherapy, if we want to simply define it, means that radiation field inside the enclosure is independent of the position of the black body inside the enclosure. So it doesn't matter where I put if I put it here, 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 doesn't matter. It won't change anything. Okay? So radiation field within the enclosure is independent of the position of the black body. Okay, now let's go and try to prove that the black body is a diffuse emitter. So we want to now, by knowing the concept of radiation isotherapy, we want to prove that the black body is a diffuse emitter. What we want to prove? We want to prove that it's independent of direction. Okay? Let's go back to the same enclosure that we had. Okay? We have like an enclosure evacuated, inside is vacuum. Okay? At T infinity. Okay, so, and again we put like a black body with a temperature of TW, very small black body. Inside TW is greater T infinity, and inside is vacuum. But we just want to add one more assumption to it. In this assumption, I'm going to say that if this is the inside of the enclosure, just a small area of the inside wall of enclosure, which is called dA, is radiatively active. So the rest of area, they are not radiatively active. The only active area is dA. Will it change anything? No. Exactly the same thing will happen as the previous case. After sufficient time has elapsed, the black body will reach thermal equilibrium with its surrounding, and the black body will reach to the temperature of T infinity. Even though not all the inside area of enclosure are radiatively active. So just a small portion of inside will be active. Maybe you said that, yeah, maybe it takes a bit like longer time. Doesn't matter, because we talked about the sufficient time. Okay, at the end, after some time, sufficient time, it will reach the thermal equilibrium, which means that the temperature of the black body will be equal of T infinity. But now the story is, at the same time, what does it mean? It means that the based on the first and the second characteristics of black body, is a perfect emitter and absorber. Okay, all the radiation is coming in a particular direction. Why? Because the rest of area is not active, so all the direction is coming in just one particular direction. But because only a small portion of our enclosure wall is active, and it has to radiate back exactly the same amount of radiation, otherwise the equilibrium will not be established. Okay, so a small part of the inside of the enclosure is radiatively active. Again, the same concept as previous one. Okay, exactly the same concept. Maximum emission absorbs exactly the same amount of emitted radiation. So the maximum emission, maximum absorption. Because in this case, all is coming in one particular direction, the absorption should be exactly the same direction. So therefore, if I want to put it in a very simply, since dA, which is this area, like the small area of active radiatively, since dA absorbing the maximum radiation in that particular direction, it has to radiate the maximum radiation back in the same direction, because the rest of the enclosure is not radiatively active and it's valid for any particular given direction. So when it's valid for any particular direction, it means that if the dA is here, the same will happen if we assume that the dA is here, the same. So we just proved that blackbody is a diffuse emitter. It means that the emission is independent of direction. Okay, that was all for our first lecture, and I will continue speaking about the same topic in our second lecture. Thank you for your attention.